we will carry on our discussions on eigenvalues and eigenvectors. So as I mentioned before, that we might have done some of the theory of eigenvalues and eigenvectors, but from more of the computational point of view. So what we are going to do in these set of discussions is that we're going to develop the abstract theory of eigenvalues and eigenvectors and some of its applications, some of important applications of it actually. So in our last discussion, we kind of proved this general assertion that every square matrix has eigenvalues. So it has eigenvalues actually. The next important thing that we would like to address in the beginning of today's discussion is that if there are eigenvalues of every square matrix, the question is that can we quantify them? Can we count them actually? That so if you have given in a square matrix, how many eigenvalues does a square matrix have actually? Okay, so this is, we would like to answer this question, that how many eigenvalues does a square matrix have? Okay. So this is something that we would like to address in the beginning. We define by spectrum of A. So if you have been given a matrix, then what is the meaning of the spectrum of A? So the spectrum of A, of a given matrix A, where obviously A is n by n matrix from the field F, which could be real numbers or set of complex numbers. By spectrum of A, I mean the set of all eigenvalues of matrix A actually. Okay, the set of all eigenvalues of matrix A. So in particular, in this part, we are interested in that what is the size of this set actually. Okay, what is the size of this set, and hence this is going to tell that how many eigenvalues does the matrix have. Let's start with some of the basic assumptions which kind of lead us towards the answer of this question. We will like make sense of it. So let's start with the first interesting lemma. So the interesting lemma, this interesting lemma says that if you have an eigenpair, and if you remember what do you mean by an eigenpair of a matrix, is that lambda is the eigenvalue and x is the corresponding eigenvector. Okay, so if I have, say, let lambda x be an eigenpair of matrix A. Okay, so whenever I'm going to assume matrices throughout the discussion, these matrices are going to be the square matrices from the entries in F actually. Okay, where F is a field of real numbers or field of complex numbers. Okay, and let P be any polynomial actually. Okay, let P be a polynomial. Okay. Then what we can show that in this polynomial, if you evaluate the given polynomial at matrix A, okay, and we know that what is the meaning of evaluating a polynomial at matrix A. So for example, if a polynomial is x squared plus 1, then the P of A means the matrix square plus added into the identity matrix actually, okay. So the P evaluated at matrix A is a matrix, okay, which you obtain by substituting the matrix into the polynomial, which you get A square plus identity. Okay, so with this meaning of P of A, or with such meanings of P of A, so when the matrix P of A, okay, is multiplied with the eigenvector x, we get P evaluated at the eigenvalue lambda multiplied by x actually, okay, multiplied by x. That is that P of lambda and x, this is an eigenpair, okay, it's an eigenpair for matrix P of A, okay, for matrix P of A. So what does the lemma is telling us? That if you have an eigenpair of matrix A and P is any polynomial, and then the P of lambda, okay, and x is an eigenpair for the matrix P of A actually. So the matrix P of A multiplied by x is going to be P of lambda multiplied by x actually. Okay, but the P of lambda is obviously an scalar actually. So this is what is an interesting result that we are going to show, that is going to later help us to determine the values, determine our result actually. Okay, that will help us to kind of answer this question, that how many matrices, how many eigenvalues does a matrix have actually. So here's a quick proof of it. Then, so if say lambda x, so it's given actually, so given that lambda x is an eigenpair of matrix A, or for matrix A actually. And so if it is an eigenpair, what we can prove is that it's going to be Ax equal to what we call lambda x. Okay, so it's going to satisfy this. How about if I compute, say, A square x? So the A square x is obviously going to be A operated onto Ax, and A operated onto Ax is going to be lambda x. Lambda is in the scalar, so you can pull it out. So you're going to get Ax. And the Ax is again lambda x, so you're going to get lambda multiplied by lambda, so the lambda square x actually. Okay, that is, if you compute A square x, you're going to get lambda square x. Okay, so inductively, you can easily prove that no matter what power you take for of the matrix A, and you operate it onto the eigenvector x, you're going to get what we would call lambda power j times x actually. Okay. So what does this also show? That if x and lambda is an eigenpair of matrix A, then x and lambda power j is an eigenpair for the matrix A power j. Okay, that's what is the first thing. So P is some given polynomial. So let's assume that P of A looks like this. So it's C0 plus C1x plus so on and so forth. I don't know, it has some degree actually, Ck and x power k actually. Okay, say x power k. This is what is really the given polynomial actually. Okay. So what would be P of A then? So the P of A then is going to be C0 multiplied by identity matrix plus C1A up to Ck and A raised to k. So this is what is going to be the matrix P of A. So what is, so with this description now I would like to operate P of A onto x actually. So let's apply P of A onto x. So when you can apply P of A onto x, what you're going to get. So this would be like C naught I plus so on and so forth plus C1A plus so on and so forth, Ck a power k operated onto x actually, okay, multiplied by x. And if this is the case, then what we can see actually. So, by distributive law, this will become C naught Ix, this will become C1 Ax, this will become so on and so forth, plus Ck a power k x actually. And with this observation, okay, the observation that you have just written. So, by the way, you can also say that a raised to 0 is matrix identity actually. Okay, so this is something that you can also define if you wish. Anyway, so this will become C naught x plus this is going to be C1 ax is going to be lambda x plus the next power is C2 is going to be lambda square x plus so on and so forth, and it's going to be Ck and lambda power k x actually. And from if all of these, if you pull out for example x, so you're going to remain with C naught plus C1 lambda up to Ck lambda power k operated onto x. And if you see, this is nothing, this is precisely p evaluated at lambda times x actually. Okay? So the P of A matrix operated onto x is giving us P evaluated at the lambda times x. That is that the eigenpair, that is that the P of lambda and x is an eigenpair of P of A actually. Okay? This is what this little result shows actually. So it's an interesting result. I would like to first recall a fact. So in our last discussion actually we showed that if you have a polynomial, so if you have a matrix A, okay, that is an n by n matrix, and P is a polynomial that annihilates, okay, so it's an annihilating polynomial, it's a polynomial that annihilates A. That is, if you substitute P into A and consider the matrix P of A, you're going to get the zero matrix. So if this is the case, then in such polynomial, okay, so in such polynomial, if you substitute the eigenvalue, okay, if you substitute the eigenvalue, so if lambda is eigenvalue of the matrix A, and you take this lambda and substitute it into this annihilating polynomial, then the P of lambda would also be 0. P of lambda would also be 0. So we proved it in our last discussion. So I'm going to use this fact actually. You take a matrix, take an annihilating polynomial, take any eigenvalue of this matrix A and substitute it into the annihilating polynomial, you're going to get 0. Okay? So let's prove a little lemma. Let's take one step, ahead towards counting the number of eigenvalues of a matrix A. So here is a little theorem, and the theorem goes like this, that consider you have an n by n matrix, and P is a polynomial, of some degree that annihilates, okay, that annihilates matrix A. That is that P of A is 0 matrix. Then following two things will happen. Number one, every eigenvalue is a root of P, so we already know it. Okay, and B is we can again show it that A has finitely many different eigenvalues. A has finitely, so it has finite number of. So if you take an n by n matrix, it has finitely many eigenvalues. How many? We don't know yet. It has finitely many eigenvalues. Okay. So what's the quick proof of it? So that if you consider, for example, the first, okay, lambda x be an eigenpair for matrix A, okay, then we just proved that P of A for any polynomial, there is no restriction on this polynomial actually. This can be any polynomial actually. This identity is true. So in particular, if I take annihilating polynomial, so for this annihilating polynomial, this identity of lambda x, but since P of A is an annihilating polynomial, so this is going to be the matrix 0 multiplied by x, which gives you 0. Okay. Now since x is an eigenvector, so it can't be non-zero, so it can't be 0. The only choice that you have is P of lambda to be 0. Okay. The only choice that you have is, since x is not 0 being eigenvector, so P of lambda is 0, and this is what that is really required. Now let's move towards the point B actually. For part B, actually we proved basically one little lemma about in our last discussion, that if you have a matrix A and that is n by n matrix, and P is an annihilating polynomial for A, so the P can have degree at most n square actually. Okay, so we proved this one result in our last lecture. I mean, you can go back and watch it actually. Okay. Now, since P is an annihilating polynomial for the matrix A, okay, since P annihilates A, which is an n by n matrix, so P can have at most what degree? N square degree. Okay? N square degree actually. So this is what that it can have. Now if P can have n square degree, then, and we know that every eigenvalue is a root of P, then how many roots this P can have? So if P has at most n square degree and every eigenvalue is a root of P, so this means, you know, every eigenvalue of a given matrix is a root of P, then from this fact it follows that the given matrix A can have at most n square eigenvalues, because the P can have at most n square degree. So if you have an n square degree polynomial, fundamental theorem of algebra tells you that it can have at most n square solutions actually. And each eigenvalue is also a solution of this polynomial. So for sure, the matrix A, so matrix A can have at most n square eigenvalues. Okay? N square eigenvalues. So kind of we have now an upper bound, okay, on the number of eigenvalues actually, that here's the next theorem, which kind of help us to have a sharp bound on the number of eigenvalues of the matrix A actually. Okay? So let lambda 1 x1 up to lambda d xd be eigenpairs. Okay? Eigenpairs for matrix A. Okay? For matrix A. So let me put this result in two parts. For matrix A, that is an n by n matrix, in which lambda 1, lambda 2, lambda d are distinct eigenvalues. Okay? These are the distinct eigenvalues. Then these eigenvectors x1, x2 up to xd are linearly independent actually. Okay? So they are linearly independent. Alright, so imagine there are d eigenpairs. So this d at worst can be equal to n square. Okay, so imagine there are d eigenpairs for a matrix A, which is an n by n matrix, and all these eigenvalues are distinct actually. Okay, then for the distinct eigenvalues, the corresponding eigenvectors must be linearly independent. Okay, this is an important thing. The second part that I would like to add, which is kind of give us a sharp bound, even better bound than bound of n square actually. So here is the result, the next result, that the matrix A that we have here, in which these vectors are linearly independent, has at most n eigenvalues. At most n eigenvalues. And if A has at most, say, n eigenvalues, in other words, say D is, can be at most equal to n, okay? Then at most n eigenvalues, and if D equal to n, then I know that these eigenvectors, n eigenvectors are linearly independent, so they form a basis for Fn. So if D is n, then this x1 up to xn forms a basis for Fn. Okay, it forms a basis for Fn. C, could be Cn or Rn. So let's read the result again. Let's see that y